is yours.
Okay, let's hope you can see my presentation. Yeah, let me see it. Yeah, can you see my presentation? All right, perfect. So basically, we'll be looking at electronic textiles just already. Thanks for all the introduction and thanks for inviting me. Uh, so the first thing we're looking at is textiles, and textiles is everywhere. So I just wanted to give a brief introduction because I know some of you might not be from this area. So textiles are everywhere. Basically, you wear textiles, and most of you possibly are wearing your underwears. That is also textiles, and everything, even car seats and random things that you have. Most of the things around you are made of textiles. So it makes a lot of sense to make these devices quite intelligent. When you look at smart textiles, electronic textiles, or smart textiles, uh, the whole idea what people think is illuminating textiles because that's what's out there and that's what's more visual and people like to see it. So you might think of illuminating textiles, but there's a lot more to it than that. So one thing, you can do a lot of sensing. So if you're doing for older people, if they want to wear some sort of wearables, right, you can use like a normal textile. There's no stigmatization in wearing a t-shirt rather than having some sort of massive medical device that you have. So you can basically wear some sort of textile, it's quite familiar, and you can integrate your electronics quite discreetly at different points. And this is quite nice because normally if you're wearing something like a Fitbit or something, it always has to be on your wrist. So example, if you want to make a measurement under your armpit, it's quite uncomfortable to put some wearable there. But with the textile, it's much more easier. Again, another thing that I mention all the time is it worth getting into smart textiles? It is estimated to be one of the biggest industries in the future. It's supposed to be 5.5 billion in 2025. So this is something that people estimate. Again, we are not sure, but there's a lot of interest with companies like Google, even Microsoft, and other companies. So the applications for smart textiles, like I said, illumination is one, healthcare monitoring is one. Then there's a lot of heating and cooling applications, rehabilitation assistance, and if you're working with older adults and things, right, getting your textiles to help you with your rehabilitation activities, that will be quite an interesting area. Recently, one of my friends basically embedded small photovoltaic cells within a fabric and used it to power like a mobile phone. He was able to power this small mobile phone using just a piece of fabric, and it's a normal piece of fabric. Uh, there's quite a few areas that kind of you look at when you're creating smart textiles. There's textile element, there's the electronic element, and there's the material element. And something that I didn't put here, there's also now computer science, because you need to actually create systems around these smart textiles. Otherwise it's a bit useless to just have your textile gathering data. Again, a little bit of a history, then we'll dive into all the cool stuff. But smart textiles basically started from basically in 1900s, so it was there for a long time. So there was all this conductive yarns for heated bed sheets and gloves for pilots, and there was quite a few from the 1900s. Then you can see the first generation of smart textiles, and the second generation, and the third generation. We'll look into it, how these generations are divided, and that's how we like to call it. Again, it might not be the right generation term, but it might not be the right way, but that's how we call it. So the first generation, as we say it, is where you're wearing the textile and you have these massive pieces of electronics on your clothes. It's like carrying a mobile phone around you, and you have these massive pieces of electronics. And this was kind of the first generation of smart textiles. But textiles, as you can see, it has these quite unique properties. So you can see a textile basically can drape around a shape quite well. So it's got these really nice properties that it can drape, it can shear, and it's not just bendable. So it's got a lot of features that make it quite comfortable. But the problem with these sort of textiles is that these electronics, they are quite hard, and they are quite rigid, and it's quite difficult. It makes it quite uncomfortable to wear. So people really do not like wearing these sort of the first generation smart textiles. If you look at the second generation, I would say this is where you integrate some sort of conductive threads or something into the fabric and create sensors and elements using this. So there's temperature sensors and pressure sensors that you can create using just smart threads, right? The good thing about this is it's quite comfortable to wear. It's quite wearable, but there's the downside of this technology is that this technique is because textiles are quite prone to hysteresis, so they cannot repeat. They find it very difficult, especially these sort of sensors, to repeat its measurement quite often. So you need a lot of electronics in order to get proper measurements from these devices. The third generation, like we call it, is the generation where you put electronics within the core of textile yarns, which is textile yarns are these small fibers that you have that you create your textiles with. So things like this. So this is a yarn, right? So it's just a yarn that you can knit or weave some piece of clothing. So the idea is to embed some sort of sensors or semiconductor dyes. In the case of MIT did some research, they put some semiconductor dyes and within the yarn itself, so it's completely integrated and hidden in the textile, so you can completely hide the electronics. This is where I'll focus my talk on, and this is where my research is on as well. So we'll look at the first type of smart textiles that I produced in my PhD, and then we'll go on from there. So here we kind of like to embed semiconductor devices, SMD chips, in the case of my PhD, a thermistor within the fibers of a yarn. So the idea is you have the yarn soldered onto copper wires, which are these wires, and then it's encapsulated with a polymer micropod, which makes it completely washable. You can chuck it in the washing machine. We've tested it, it's completely washable. Then we cover it with packing fibers and a covering yarn, which kind of protects it further, as well as it kind of makes the electronics hidden within the fabric. Here's a small video of the method we have currently at Nottingham Trent University, the Advanced Textile Research Group, of making the soldering using an automated system. So you kind of first you remove the, so it's enamel copper wire, so you remove the enamel, and then these are miniature copper wires, and then you put your solder paste on there, and then you have a pick and place machine to position your sensors. Then you solder it, and then you add a little bit of resin to protect the solder joint, which is quite fragile at this point, and then you go to the next step. The next step is to completely encapsulate it within some sort of structure. So it depends, the structure depends on the electronic component and its functionality. So in the case of certain sensors, we kind of have this certain parts open or certain parts closed, certain shapes depending on the sensing element that we're using. So in the case of thermistors, we just have an encapsulation, and this encapsulation basically protects the entire chip and the interconnects from mechanical damage, and it makes it washable. Then the idea is to send it through a covering machine. That's also facilities we have at NTU, and also these are commercially available covering machines. And this covering machine basically creates some sort of textile. This is a knit braided structure. It creates a knit braid structure around the electronics, making it completely hidden. Once you have the yarn, you can't really see the electronics. So you can see this is my finger. So you can't really, so this is another yarn with a chip, but the chip is somewhere here, right? You can't really see it unless I show it. If you touch it, if you go very smoothly, you might be able to feel it tiny bit. These sensors are really tiny. So we're talking about 0.5 millimeters, tiny, and it's almost like a speck. You don't realize, because even with our normal clothing, there are some areas that are hard that we don't notice. So this kind of acts like that. So it's completely hidden. The good thing when it comes to sensing, yes, there's a certain bit of uncertain. There's a the sensors have to be calibrated, because obviously the sensing element is not in direct, especially when it comes to temperature, it's not in direct contact with your skin. So if it's not, because there's this fibers in the middle. So you need to calibrate it accordingly. And this is a problem. This is not a problem if you calibrate it. So certain things you need to look at is obviously the step response time, and everything is not really affected. It's about 12 seconds, which can be a problem if you're doing fast measurements, but for most applications regarding temperature, this is not an issue. Again, it's completely washable. You can put it in the washing machine. This is just a picture of me putting it in a beaker, and it completely stays hidden. Uh, and it has no impact with moisture or humidity, so it's quite stable in any sort of environment. For the PhD, so because Arong mentioned that you're working with older adults, and something that's there not with only with older adults but with a lot of people is a lot of people get diabetic foot ulcers. So there is some research by David Armstrong that has done some research where you can monitor foot temperature, and you can see before an ulcer occurs, like 2 weeks before an ulcer occurs, that you're more likely to get an ulcer depending on your temperature changes between the 2 feet. And this is something that we did. So I worked with a Silicon Valley startup to develop socks for diabetic ulcer detection. And this was quite an interesting project. And we had like sensors in different locations. Uh, this is not the only application that we worked with. So we also worked with temperature sensing for Raynaud's disease, which is a disease that, some people, when they touch something cold, they get a real pain, kind of shock to the system. So we wanted to create some sort of glove that can detect and help them. There's another project that we worked on again with a sock that was to create a tool for the military. There is this thing called non-freezing cold injury. It's not like it's unlike frostbite. The difference between frostbite and non-freezing cold injury is this non-freezing cold injury occurs when you're exposed to temperatures about 5 to 15 degrees or something, or 5 to 10, 15 degrees for a long period of time. You get these injuries, and this can be really bad for the military. And I think you guys are in Canada, so it might be normal. I'm not sure. But this was a problem for the British military. Another thing we developed was a wearable thermograph. So the idea was to create a map have a map of temperature sensors for wound dressings. And when a wound is going bad or good, you can see that. You can if you have a thermograph, you can see the temperature changes, and from the temperature changes you can estimate where a wound is going good or bad. This is mainly useful when it comes to wounds like ulcers, which are there for years. So every time they have to go to the doctor and show their wound to see if it's good or bad. So this kind of system could help monitor these wounds. Here's a small video of just a friend of mine just playing with this glove. This is a really old video, so I found it somewhere lying around, so I thought might as well include it. So what happens is she just touches the fingers of the glove, and there's some sensors in the glove. We have Bluetooth connectivity, and then you just see it immediately change the temperature when she touches the different fingers. Again, you can do much cooler stuff now, but it's just a small thing we wanted to showcase. More recently, we put movement sensors, and that's something might be interesting for you guys. So we put accelerometers within socks. I keep working with socks quite often. I don't know why, but I think everyone wants socks. So we basically put accelerometers in socks. Again, we have the SMD component, which gets encapsulated, and you create the yarn. It's completely hidden, and once it's created, you can position the sensors. These sensors are a bit larger because these components are a bit larger, so the yarn is a bit more thicker, but you can see the sensors are somewhere here, here, here. The interface electronic unit, which is quite large, is right here, but that one can be made smaller depending. But this was in the focus of this paper, was more on the sock, and you can see it's completely flexible. And we tried it on more than 15 odd people, and no one felt uncomfortable with the sensing element. So it's quite flexible, and this is inside out. You don't really see the electronics, it's hidden, so it's really nice. And once we did that, we tested it on different gates. So we asked people to mimic gates. So you might have already seen that there are some diseases that cause gait defects. So if you have a stroke, for example, right, you have a hemiplegic gait and you have certain ways. There's step edge gait where you lift your legs so high, and there's like stomping gait, which is with diabetic patients. They just smash their foot because they don't have sensation in the foot. So what they do is they keep smashing their foot, and that can cause damage. So we wanted to see if this only this sock without any interventions. You asked the person, we asked different people to wear this sock, and we trained an algorithm and by LSTM, and then we wanted to see if the by LSTM can actually detect uh, when we use it for a new group of people, if it can detect these gates. It was successful for some gates quite well. It did quite well, but for things like step edge gate, it was quite difficult because most of the step edge gate was classified as stomping gate. Because in the case of step edge gate, the only motion is leg goes up and down. It's almost, because we were using accelerometers, it's quite difficult to mimic this. Now we are again repeating this experiment with IMUs, and I think the measurements will be much better, and we'll have a better accuracy with these sort of with the IMUs. But you can see already it showed quite a good accuracy rate, given that we tested on different people, and it showed like diplegic few gait. It was able to classify diplegic, hemiplegic, normal gait, shuffling, and stomping gait quite well, but it was not able to do foot slap because there's a change of acceleration in the case of foot slap and the step edge gait. So those two are confused as stomping gait, which is something we're working on currently. Okay, so the next bit that I want to show is I just want to show you different technologies that you can use and see if there's some sort of thing that you guys want to do. Uh, Next thing you can do is integrate flexible chips, flexible PCBs within the fibers of the yarn, and then push an SMD chips on that. In this way, you can get a little bit more electronic functionality. You can get it with the yarn technique as well, but this is a little bit more different sort of technology. You still have the polymerase in, and then you have the yarn cover. So this one, we created an individually addressable LED strip design. So we used a technique called Charlie plexing to address multiple LEDs in a small strip. So, and then we created the flexible PCB for that. Again, this was all industry fabricated. This we did not. So we wanted to create. So the objective of this one was to actually create everything using industrial methods, so it can be mass produced. And one thing we can see is you can easily create this sort of so this you use a flexible PCB manufacturer, they can create the structures, and then we use the normal pick and place machine to push in the LEDs. And once that was done, you can use a normal laser cutter to cut these strips through. And once it's done, so this was some work I did at Microsoft, and they did not have some of the textile equipment, especially the covering machines. So we kind of built our own covering machine using just stepper motors. So it's a very crude design, but it works. So it's something that can put the electronics in the center. Once you have that, you have these LEDs that are individually addressable, and you can program certain things, and you can say which areas to light up, and you can use things like messaging. Once that's done, we inserted these LED sort of yarns within a fabric using normal weaving machines. And then once that was done, we created the final fabric, and you can see you can have different designs. I had my name on it, but I don't have the video of that anymore. So it's completely, it's a normal fabric, but it's got things coming on. So you can use that for messaging sort of applications, like different applications. The third technique that I want to introduce is you can also insert things like flexible PCBs within the yarn itself. Like if you think the SMD devices are too thick, even though it's 0.5 millimeters or 1 millimeter, you can put completely flexible, really thin structures in the yarn, flexible sensors, We put flexible temperature sensors in the yarn the same way. We looked at different manufacturing machines. So we looked at there's different machines of doing the covering, and these are all industry machines. And we went, in some cases, we also went to the industry partners and asked them to do the covering for us. So we wanted to see if our techniques are robust enough to withstand industry machines. And you can see we looked at three different covering methods: nip braider, braider, and double cover. And all three worked quite well. So most of the stuff you can find on the paper. All three gave a really good cover, and the functionality was not affected. But the visual was different for each one. So I think the suture braiding method produced the best sort of looking yarn. Again, and then I think the double cover was next, and the knit braider. The thing with these flexible structures is most of the flexible sensors can bend a lot, but they can't drape, they can't shear. So shear is basically this movement, right? So you can't do that with flexible sensors or any sort of these flexible electronics. Uh, that was a problem, and we are looking to at addressing that now. Ways of creating it in such a way that it's completely flexible and also thin, so we can create these yarns extremely thin rather than having some sort of even a small dot in there, so it's completely integrated within the textile. We did some of these tests. We just did some a random rudimentary test with these yarns where we just used it for uh, a gym workout, where for initially you can see the yarn wasn't worn as soon as you wear it, and then it was taken off when the person was doing some exercises, and then he wore it again. You can see the temperature increase, and then the same thing repeats itself. So you take it out and again go. So you can see the response of the sensors. They respond quite quickly as soon as you take it off, and they respond quite fast as soon as you put it on. And it can actually detect like there's changes of temperature when after you do something like a bicep curl for a while, which could be useful for different applications. There are certain things like we can put active electronics in there as well. So we haven't really put this, but we've looked at creating transistors and transimpedance amplifiers using flexible transistors and transimpedance amplifiers to put it within the yarns itself. So the idea is to have your sensor conditioning circuit in the yarn itself, so you don't even have, and it can be very close to your sensor, so there's no drop in signal, or there's no uh, noise. The signal will not gather noise before it comes to the sensor conditioning circuit. So you can create these sort of structures and put it right next to the yarn itself. We looked at it for different applications. So we tried to create some sort of touch system that we want to use this transimpedance amplifier to monitor. uh, the next one I want to look at is, this is what I'm working on currently. Just wanted to give an overview on this one as well. This is actuating textiles. So the same concept, we keep it at the yarn level, and we want to create actuation in the textile. We think this is the next generation or the next iteration of our technologies. Uh, the idea is you can create different structures. So we've created an actuating textile, and this is currently under review for a journal, and we've got the comments recently. The idea is you can create a textile structure. So you have this yarn where when you put some air pressure in, depending on the structure, it inflates at a precise location we have already assigned. And once you put it in a fabric as well, you can get these sort of bumps or this feel at different locations. So this is quite good for a lot of applications. Obviously, VR gaming and any sort of gaming industry or movies. This would be really useful if you're watching a movie and you can feel things on your t-shirt when certain things happen. Another area is something in rehabilitation. Some people want to give some feedback to people. You can use this as well. Then there's compression therapy, lymphedema, treating people with lymphedema. You can provide precise compression at precise locations, which would be quite useful. uh, what I got inspired when I was doing this initially was this talk by this person called Ted Eagleman, where he was showing how you can use your t-shirt to actually communicate. So for people who are deafblind or have any sensory impairment, you can provide signals. So you can provide certain vibrations in your stomach. You have the sensing element next to your stomach that, and you can train people to listen through your skin in a way that, when you say hello, a certain vibration goes and so on. And he trained someone to listen and communicate within 2 or 3 months, but he used motors, and we thought we can do it slightly differently. So again, a small demonstrator of a VR thing. So it's very crude VR demonstrator. We are not software people. You can see that. So it's a very crude VR demonstrator, but you can see when it rains, you can feel it on your hand. And when you wear it on top of your hand, it feels as if it's raining. We have other things as well here. So you can create some sort of vibration as well if you want, or certain signals in a different way. So you can change the frequency. You can play around with the frequency and provide any sort of feel that you want, that you want to get. We haven't explored it too far. What we do is we create this stuff, and then obviously people like you or someone who wants to develop it further can take it. We've done more recently, we've looked at things like bending actuators. The idea is to provide, so you can see this. So it completely bends, so it can be supportive. And this is the same technology as before. So it provides the haptic feedback, but much larger bubbles. We can change the bubbles size as well, depending on the application, and we can play around with that. So the bending one is quite useful if you're doing rehabilitation, and if you want to assist people with their movements, you can use this bending actuators to provide the assistance rather than having some sort of exoskeleton which is quite uncomfortable to wear. So if you just wear this bending, this sort of textile, then you can assist. So if you look at physiotherapists, all they do when you have an injury is they first assist your movements until you gain some strength, and afterwards they give you resistant movements that to build up that muscle or wherever. So the idea is you can use a textile to do that rather than having to go to your therapist all the time. So lastly, I want to just say that, we've done some work with biocompatible smart textiles as well. And I think this should be the future, but it's just taken some time because it's quite difficult to make this stuff. We've made like stretch sensors using eco-friendly materials like coconut oil. So the idea is, because textiles and electronics are two of the largest pollutants in the world, if you combine the two, you're going to create such a mess, right? So we need to make sure that we have methods of doing sustainable ways of creating it. So we are looking into more eco-friendly things as well at the moment, trying to see if we can create some sensors. Funnily enough, the sensors that we created with the coconut oil, you can see it from the paper here, performed much better than other stretch sensors that are normally produced with things like heptane, which are harmful chemicals. Again, so the important things to consider if you guys want to get into smart textiles, wanted to keep it a bit short. I hope that's okay. So things to consider is conformability. So that's number one if anyone wants to get in. So you need to make it completely conformable. Otherwise, no one's going to wear it. And if it's not conformable and it's not comfortable to wear, you're not going to wear it. You need to make sure the electronic functionality is not affected, because if it is affected, the electronic functionality, then you have sensing elements, then it's really difficult to get any measurements out of it, right? So you need to make sure that you create the electronics in such a way that it's completely protected. And normally textiles are quite subject to a lot of mechanical. So if you look at your t-shirts or whatever you're wearing, it gets rubbed on your chair, it gets rubbed everywhere, your hands can knock on it. So there's a lot of potential for damage. So you need to keep this in mind. You need to conceal the electronics, because that makes it quite nice in a way. If the electronics are hidden, you can be wearing some sort of sensing garment or something. If you have a certain disease that you don't want people to find out, you can conceal the electronics and it stays hidden, which makes it quite good, because then there's no stigmatization for wearing these sort of devices. The other thing, it has to be durable. Like I said, it has to be machine washable, environmentally friendly, and most importantly, cost is a important factor. So most of the stuff that we do, we make sure that the cost is not too high, because textile production, if you look at textiles, it's quite cheap to make some t-shirts. It takes quite a low, even though you buy your t-shirt from Nike for 50 pounds, the fabrication cost for Nike or the factories is like a few, maybe 2 to 3 pounds or maybe 5 pounds maximum. So you need to keep the cost down so the consumers will get it. So that's something we try to do. So even with our SMD devices, and these devices are quite cheap, so to manufacture. Yeah, that'll be it. Is there any questions?
Okay, great. Thanks, talk. Any question from the audience? You can either raise your hand or you can just directly unmute your mic. I think the first question is always the hardest. Maybe let me just start the process. Yeah, it's very fascinating, the technologies that you develop and some of the demonstrated application. So it seems that the size of the electronics you can embed in the fiber is obviously limited by the thickness of the yarn. So do you see that will be a fundamental limiting factor ultimately? Or you see, for instance, like you can build a network of those small devices and to enable more complex functionalities?
So like you said, yeah, so at the moment, one of the limitations is the size of these chips. So if you get it smaller, we can integrate it. If it's not small, then there's a problem. But one thing we can do is we can have most of the connections through wire, because we have this miniature wire system running through, and more complex devices like maybe Bluetooth units and microcontrollers that are slightly larger that can't go in could maybe be integrated. What we are thinking is integrated into things like buttons or buckles or some sort of thing that's already an accessory, but it's connected and we have the sensing elements running through, and even the batteries. So there are these flexible batteries that you can use, but if you want to create like some sort of good battery, the idea is to keep the textile element as it is and then work around that.
Mm-hmm. I see. But
Try
if
not to.
you yarn, once you embed the electronics, they're gonna be covered and insulated, right? So the only way you can get the signal out would be at the endpoints.
Yeah, so that's something that's there. So you have the signals that has to come from the endpoints. So that's, we can take the wires out from the middle as well if it's needed, but ideally you want the yarn running all the way through, and at the endpoints you have some sort of connection, maybe to a button or something. On the yarn structure itself, you can try to play around. So either you can use the flexible PCB sort of stuff. Again, there is a limitation, obviously, right? Because of the amount of stuff we can design on a flexible PCB compared to a normal PCB, which is multiple layers. We can have multiple wires running. So if you look at the accelerometer, right, we have about 4 wires coming out. So the IMU stuff that we're developing now has about 6 wires coming out. So we can do devices up to maybe 8 or 9, even 10 wires, we can do it. But yeah, there is some limitation which you need to work around. So you can't create a whole computer system, for example.
I see.
That's
Okay, that makes sense. So I have also seen, I think, some of the students or researchers in the group, we have visited a lab in Windsor, headed by Dr. Trisha Pomako. They actually look into depositing conductive material on existing fabric. They also demonstrate like something like a conductive ink in over like printed over papers. So I wonder, what's your comment about in terms of technology trend, like advantage or disadvantage? Like one is like you actually embedding electronics inside the yarn. The other is that given an existing piece of fabric that you actually kind of deposit or print on top to enable maybe sensing or actuation. I don't know whether actuation is possible, but sensing is probably visible, or at least you can do some kind of smart LED, things like that.
Yeah, so I think depositing is one. Depositing, there's difficult things as in the surface roughness. So if you look at like PCBs and stuff, they are quite smooth, right? So when you look at fabrics, if you look at your cloth, if you look at it close up, it's quite fibrous. You get fiber. So depositing is not as easy. One, some people have found different ways of depositing, and that's fine. That works. The other problem, again, you can create more structures with depositing. Again, you can't create multiple layers. That's not going to happen like a PCB, but you can create some structures. One of the biggest problems with depositing stuff is that if you like, my hand is currently sitting on top of the chair handle, right? So it's rubbing against something all the time, textiles. So the problem with these sort of structures, if it gets completely, abrasion is huge for smart textiles, because every time you're sitting your chair, so your trousers is always rubbing on the chair, it's rubbing against some sort of surface. And this, even your skin, right, it rubs against your skin all the time as well. So your textiles, so this can, this can delaminate most of the time, unless you really, again, it depends on how you create it. So I have not seen their work, but normal, from what I've seen, most of the stuff that's on the when it comes to like applications, right, it's quite difficult, because if that's one reason why smart textiles are not out there yet. It's not, it sounds pretty cool, but it's not as easy because there's so many different areas to look at.
Mm-hmm. I see. That makes sense. Any question from the audience?
Yep.
I have a question, Rong.
Go ahead.
Paula. Hi. Thanks
Hi.
so much for your talk. It's so interesting to see the current state of the technology and where you're taking it. So I'm one of the faculty in SMAP, and I'm a humanities person. I'm not an engineer. So I'm just telling you that for when you answer my question. But I work in interdisciplinary teams, designing different kind of technologies. One of the things I was working on, and this was with Rong, was about 8 years ago, and we were trying to create the potential to do rehabilitation exercises remotely, where technologies such as sensors in your shoe could help measure how well you were doing the exercises that were given, like the sit to stand and walking. So we were trying to measure acceleration, gait, but also balance. And so we were trying to put pressure sensors in. Well, we were just using kind of inserts into the shoe. We weren't using socks. Can you talk more about your socks and what other kinds of sensors you think could be embedded in those, like whether they could be measuring balance?
So one thing with acceleration, you should be able to measure balance as well, right? Because there will be, depending on where they move, so they should be okay. So currently we are doing IMUs, and I think IMUs would be quite useful for this, because we are developing the IMU socks. I need to do the trials, so we are repeating the same trials, but for IMU. And our idea at the moment is use it for do the same sort of stuff to see if we can get these gates. And with IMUs, you get the accelerometer as well as the what do you call the angular stuff as well. So you can use you have the accelerometer and the forgot what it is.
So you'll get like the changing weight distribution.
You can see the change. Yeah, you can see the changes in that, and we have a magnetometer as well in there, so you can see that one. So you get a few more measurements. We can produce socks. Again, it depends if we get a grant or something, right? We can produce if we have something depending on what. We can send you some of the socks we have, but it's a bit used, so it will be a bit used. But it's definitely possible, right? And you can use the pressure sensors is a good thing. We are currently doing some work with pressure sensors, but it's still tied to an NDA. So we are doing some pressure sensors as well. So we are working with a company for that. And And that's a possibility as well. So we haven't looked at balance, but there was some research with IMU sensors for fall detection that's already published. I wasn't part of that work, but we are using the same sensors. But it was in my previous group basically.
Yeah, that's interesting. I think we were working with the physical therapists and OTs trying to think about what kind of measurements did we need that were going to be sort of as accurate or akin to human observation, which is a really interesting question, right? To understand how patients are doing their exercises properly. So that's part of our consideration, right?
That's one of the grants that I have is also linked. So recently I got a small grant. It's not so much savers, but it was basically to create a textile for rehabilitation assistance and monitoring. So and we are currently working on it. So we are using the accelerometers as well as our other technologies, the movement stuff.
Oh, great. We'd love to have those citations so we can follow your work. Thank you.
When it comes out, we should be able to share it, send it over. Yeah.
Awesome. Thanks so much.
Yeah.
Any questions? So I'm a little curious about the actuation. So are those air bubbles?
Yeah, those are air bubbles. So
Okay.
we decided to go with normal air bubbles for now, but we can do other liquids as well, but air at the moment. Yeah.
So would you concern that over time that the air will escape or whatever liquid are going to escape from the encapsulation?
So the air, that's so at this point, this technology, so we have created it and we've just had a draft. So we are looking at different materials of creating this technology. We are currently exploring that for part of the grant. So the idea is obviously it won't be as washable as the other ones, or it might be because we're looking at the moment we're looking at a certain material that's a bit more harder and that can withstand some sort of washing cycles. That is also we are working with another company that's interested in this for compression therapy. There is a problem. Air going out is not a problem because we have miniature air pumps, so it just keeps pumping in. So it shouldn't be a problem. The only concern is it's if there is some sort of hole in one of these, right? Then the air just and it's a issue at the moment we're trying to fix how to prevent it. And the good thing of having the textile structure on top is kind of protecting it as well. So good there. We've tested these ones for these samples actually with two different materials, with some with graphite and some without graphite powder, and the samples were able to last 10,000 cycles in normal expansion. So we haven't still tested it on people yet because I didn't get any. So the idea is to write another grant hopefully and try to.
Mm-hmm. So in the like a soft actual skeleton field, like people have used air bubble or water, are there other fluids that has been investigated?
There are certain fluids that I want to try, so that's something we are working on. So one thing with air, as you can see, if you have a fluid that's not as compressible, right, then the feedback will be more enhanced, and we'll feel it more. So that's why we want to try different stuff, and it should. So we are testing different things at the moment, and that's part of the person working for the grant is currently looking at this. It's an open area for us at the moment.
Okay. Can you move to the confusion table slide?
Yeah.
So you have several types of gates, but you have the last row that is like none of those, right?
So
last column.
Yeah, the last column here. Yeah. So I'm not the computer scientist who did who was working on this stuff, but I can try to explain. So you mean what these values are, right?
Right.
So here it's I believe the percentage that was correctly classified as diplegic compared to the rest on this end. Well, I remember this was some time back, but this one was out of so this one was these percentages. Best thing is looking at the paper, because I wasn't the computer guy who did the classification and the LSTM by LSTM stuff. So it was basically, this is the final percentage and the errors that we got. So this was the percentage that was correct and not correctly classified. And here was basically, I might be wrong, don't take my word for it. This one was the one that was from all that was classified as diplegic, what was correct. That's the percentage. And this one is what was wrong compared to that, as far as I know. So
it's kind of weird, because typically in the confusion matrix, the diagonal, which corresponds to, for example, the ground truth is the pelagic gate, and you classify it as the same. That diagonal tend to be very big, right? Here you have a diagonal which have below 10%.
This one, you mean?
That's not quite consistent with the actual numbers that you have. It looks like 625, 24 maybe out of 1,000 or something like that, right?
Yeah, I think the percentage was.
Yeah,
I think the percentage was. It's something I need to, because again, we do the stuff and then hopefully we find a partner to do the
and also there's also issue like typically want to do this. Oftentimes we'll have a now class, like you would also want to test if the person does not carry out any of those gates, then whether the system will be able to misclassify it as one of those known classes, or it will be able to.
So we had the normal gate as well here.
Okay.
So we had the normal gate and we had the different gates, and then we had the normal gate, and we tested it on different people, including different foot sizes, including females and males, and we and different weight categories as well. So it went from 6 to 11. So everyone walks quite differently as well. So that's something. It was interesting because we found it was with 3 of the sensors, we didn't. I wasn't expect that the accuracy is not that high compared to all the stuff, right? But given that we're using accelerometers only and nothing else, this was we thought it was quite a good number.
I see. Interesting.
The paper is here, so the classification bit was written by the what do you call it? By a colleague of mine, not a colleague, but someone we work with. So.
Okay. Well, we do have students with background machine learning that we can certainly work in this line of, like, once you have the sensor measurements, we can think about what the good model to be able to apply for the specific task.
That would be ideal, because at the moment the thing that I don't have is the machine learning background, and also we have a computer science group, but it's better for us to work with multiple people, so we can get all the data and we can send. So that's what we did last time. We got all the data, and the person I think tested different SVM by LSTM and something else, and then he came up and he showed the results, and the by LSTM performed the best, and something else as a CNN as well. So he used a CNN. And that's something we can actually do. With the measurements that we have, we can send it over, and you can see if you can make some changes. And we've been actually looking now with things like recently we did a very basic one. One of our students, well, for things like if you have what do you call this, ankle surgery, the ACL surgery, and before and after surgery, you can detect that with people that walk. So you can detect it from the people's walking pattern, as well as the way they do certain exercises. You can say this person had an ACL injury, this person didn't, which was quite interesting for us.
Mm-hmm. Yeah, that makes sense. The gait pattern would change, right?
Yeah.
My last question, you talk about the 3 generation of smart textile. So in terms of production or like maturity, like technology readiness, where are we at?
So when
are we at?
Yeah, when it comes to this this yarn technology, we are kind of at like TRL level 4, somewhere around 4 or 5. Again, we have this my previous professor was working with this. This was his side, like, you know, they putting sensors in yarns, putting the chips, was basically that's what I did with the PhD in. So they've been developing it further. They have a machine to do it, so they have this machine that actually does this. This is a simulation. They have certain problems with it as well. When it comes to production, they have to, like, you know, play around a little bit. When it comes to certain technologies like this one, again, this one I don't know where it is at TRL level wise. We did this with Microsoft, and once I left, I saw the patents, and that was it. I don't really know what they're doing. I have the authority to talk about it now, so that's all I know. So again, you can produce it. So this one, most of the stuff is from industry. All the steps are industry manufactured. So this is from the industry. You get it made, you design it, you send it, they get it, send it over. You can use a pick and place machine, which is normal for any engineering application, to position the LEDs. And it's not rocket science to do this. It's not very difficult to do it. With the flexible structures, again, flexible sensors are the difficult. So you can produce sensors, but they have deviations, right? So this is the issue with flexible sensors in general. And there are certain ways around it. And we have a really cool thing I couldn't show because it's still under, we are writing a paper, and I'm not the only person. And that would have been really interesting for you guys because it's a new way of doing interaction. And that again, we're using completely flexible sensors, and that one is not ready for production. I would say it'll take maybe 2 or maybe 3 maximum. With temperature sensors a little bit more, but with other sort of sensors it's a bit more difficult. One thing we like to do is we like to use industry machines, right? So we are almost there. So if someone wants to pick it up and run, we still haven't got any investors or companies investing yet, right? The idea is that we have the technologies, we've got the patents for most of this stuff as well. We are with this one. This is quite early. This is what I'm doing now. So what, maybe about 2, but this one already we've got some partners that are interested. We have to see how far we go with this. So that's it depends on which technology.
I see. Yeah, that's very interesting, and you certainly have a lineup of different readiness levels. Any quick question from the audience? Okay, if not, let's thank Dr. Lugoda for the wonderful talk, and we look forward to opportunities of further interaction.
Yeah, thanks a lot for having me. Hopefully we can do something. Yeah, sounds good.
Okay, thank you so much.
All right,
Thank you so much.
Bye.
Okay, good night.